Okay, so since vector spaces are like these infinite sets, we want to have a way to describe them as a finite set. And what we're going to call these things are bases. Okay, so if I have a basis, I have some set of vectors, right? So let's call these things v1, v2, out to vn, right? So v1, v2 out to vn. They're going to be in some subset. They're going to be a subset of some set v, where v coupled with addition is a vector space. Okay, so it has to meet two criteria. So this is such that one, S spans v. That means that everything in V can be written as a linear combination of the vectors in S. And two, S is linearly independent. All right, so by definition, this means that if I make a linear combination of the vectors in S and get the zero vector, then the coefficients of the linear combination all must be zero. Now, that also means that I cannot combine any vectors in S linearly to make another vector that's in S. Okay, so there you go. So if that's the case, then we say that S is a basis for V. Okay, so now we found a way to describe V using a finite set S. And the idea is V is just all of the linear combinations of S, and S is the minimal spanning set. We'll get into that minimalness there in a little bit, but it's the spanning set that's linearly independent, at least at this point. All right, so we consider our most common vector spaces, things like R3, to have what we call standard bases, and they're kind of like trivial. Like if I have the vector 1, 0, 0, 0, 1, 0, 0, 0, 1, it's pretty clear that I can take these three vectors and create everything that's in R3 through linear combination. If I have the third degree polynomials, the standard basis there would be 1 x squared, and x cubed. I can make a linear combination of these and get all the polynomials of degree 3 or less. If I have 2 by 2 matrices, the standard would be to put like 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1, and it's pretty clear that I can combine these linearly and get everything that's in the 2 by 2 matrices. Okay, so typically we represent a vector according to a basis using its coefficients. And that once you have a basis, that vector is uniquely represented by those coefficients. So this is a theorem. Say that S of has V1, V2, out to Vn is a basis for the vector space V. Right? We're going to let U be some vector in V, right? And the theorem is that U can be U can be uniquely, spelling, there we go, uniquely represented as a linear combination of the vectors in S. So the idea here is there's only one way to combine these to get U. Okay, so we're going to prove this. It's pretty straightforward. We let U be the linear combination C1V1, C2V2, out to CNVN. And then we say, well, what happens if U is a different linear combination? D1V1, D2V2, out to DNVN. All right, so then we just subtract them, right? U minus U should give me, well, let's see, that should be C1 minus D1 times V1 plus C2 minus D2 V2 out to Cn minus Vn, or sorry, Dn Vn, right? But since this is the zero vector, that means since V1 through Vn is a basis and thereby linearly independent, this means that Ci minus Di has to equal 0 for all I, which means that C1 has to equal D1 or Di for all I, which means that the representation is unique. Because if I try to make two different ones, they end up being the same anyway. All right, so that's uniqueness of representation of the vectors in the vector space given the basis. There's only one way to do it. Okay, so let's take a quick example of this. All right, so let's say we have this set S where we have the vectors 1, 2, 3. We have the vectors 0, 1, 2, and the vector -2, 0, 1. And we're going to say that this is a basis for R3. You can check that and kind of throw it through, MATLAB, and see if you get the identity matrix if you use this as the column space. So our idea here is that if I take a vector U, right, and let's make that thing 1, 0, 0, something simple, then C1 times 1, 2, 3 plus C2 times 0, 1, 2 plus C3 times -2, 0, 1 should equal the vector 1, 0, 0, right? So we can build the system of equations. C1 minus 2C3 should equal 1. 2C1 plus C2 should equal 0. And 3C1 plus 2C2 plus C3 should equal 0. Right, so this as an augmented matrix is 1, 0, -2, 1, 2, 1, 0, 0, 3, 2, 1, 0, and you can check if you apply Gauss-Jordan to that, we get the identity on this side, and the solution column is -1, 2, -1. So this vector in the standard basis is 1, 0, 0. Using this basis, its coefficients are -1, 2, -1. So it is a different representation under different bases, but that representation is always unique. All right, so we're going to get kind of to this idea that not only are these bases spanning and linearly independent, but they're of a particular size, and that size is minimal. Okay, so The theorem says this. The theorem says if S with V1, V2 out to Vn is a basis for V, then if T is a subset of V, such that the set T's size, so the number of elements in T is bigger than n, which means the size of T is bigger than the size of S, then T is linearly dependent, which means it cannot be a basis onto itself, right? So any set that has a larger size than a basis for V has to be linearly dependent. Now, the proof for this is kind of like tedious. So what I'm going to do is I'm actually going to pull up the notes for that and kind of walk you through it, because me chalking this all out with the marker is just going to get way too confusing. All right, so you can see here at the top in our theorem is there, and then we start with our proof, okay? We start by saying we're going to let this S, now I've made it size M instead of size N, so S is kind of like the T in our theorem here, right? S1, and it is larger than N, right? So that's what we want. Okay, so if we look at the next line here, we're going to make a linear combination of the things that are in S. Why are we doing that? Because we want that linear combination to come out as 0. Oh, there's a little glitch there. Why don't we fix that? All right, so let's fix that little glitch. We forgot that there's a little extra doohickey there. All right, get rid of this, and boom, we're back in action. All right, so that should be a KM, right? So we have made, oops, oh, it's still ugly. All right, let's fix it again. See, you'll get good notes from me. There we go, make that an underscore, and all right. Now we fixed it. Okay, so there we go. So we've now made the 0 vector a linear combination of the things that are in S1. Okay, all m of them, and there's more than n. Okay, so here's the thing. The things that are in S1 are also in S, or are also in the vector space, so they all are a linear combination of the things in S. So this is what we state here. Like U1 is a linear combination of the things of all the V's. U2 is a linear combination of all the V's. Um is a linear combination of all the V's. Okay. So well, that's going to get interesting. Now we're going to establish this thing. So we've got these K's, which are with the U's up here. And then we have these C coefficients, which go with the corresponding V's, right? So what we're going to do is we're going to make a coefficient called a D. D is going to be the, so D sub, I have it as D sub 1. Wow. Let's fix that too. Should be D sub I. All right, so that's better. The D sub i's are going to be like the C i's times the K's, right? So what we're doing here is we're going to make these D's, and they're going to not be important right yet, but they're going to come up. All right, so kind of looking at what we've got going on here, right? We have that all of this has to equal 0. But each of these can be expanded into things in S. So we're going to say K1 is U1, which is this. So K1 times U1 plus k2 times u2 expanded down to km times v, the um expanded, right? So we've made those expansions, and that this is still equal to 0. Okay, to even expand further, we distribute those k's through. And now we're starting to see something here, because the k's get distributed through, which puts the k's next to the c's. Okay, which is like what we were talking about up here with the d. Right, so the k's distribute through, and now we have this big long sum of vectors in v is equal to 0. And we kind of pivot. We put all the v1s together. There they are. We put all the v. So we're basically making a transpose here, right? All the v1 coefficients are going to get put together. All the v2 vectors are going to get put together all the way down to the vn's, right? So this is going to make one huge long coefficient in front of v1. Okay. So, and then another one in front of v2, and another one in front of vn. Now, each of those long coefficients happens to be what we call the d. This is the string of coefficients that go in front of d sub, or v sub I. So here, this whole equation using those d's becomes d1, v1, d2, v2, d, and vn, which is still the 0 vector. Now, S is a basis. The v's are the vectors in S, which means that d1, d2, dn all have to equal 0 because it's linearly independent, because it's a basis. Which means that each of those d's is equal to 0. Now, this is now a system of equations. This system of equations, the k's in this system are the variables, right? So this is a system of equations that has m k's. That's my variables, right? Now, the equations, the number of equations that are here is that there are n equations. There's one for each of the d's, and there's n d's. This isn't true. We have to fix that. Because from the very get-go, we said that, in fact, there we go. That's not true. We said that m is in fact greater than n, right? M is the size of my new set. M had to be greater than n. Okay, so you can go back, trace that all the way up to the top. We said that m had to be greater than n. There it is. So we're saying that again down here. All right, so if I have a system, as we just said, that has m variables, all the k's are variables, every u vector got a k with it. I have n equations, right? So all the c's, or each of these sums, all the d's actually, produce an equation, and each of those equations are there. There were n d's. It's, d from 1 to n, because there's one d that corresponds to every v in the basis. Well, if m is bigger than n, then this thing has to have n minus m free variables, at least. So if you run this like using Gauss-Jordan, you're going to get n minus m noisy rows. If there are n minus n noisy rows, the system doesn't have a unique solution. There's something that has to be parameterized. So if it doesn't have a unique solution, then 0, 0, 0, 0 for all of the variables, right? All the C1, K1, K2, Km is not 0 for all the variables. If K1 through Km is not 0 for all the variables, then the set S sub 1 must be linearly dependent. Okay, why is this important? Because if that set is linearly dependent, then it's not a basis. So if a set is bigger than the basis, it has to be linearly dependent, which means the set in and of itself cannot be a basis. Okay. So rather than doing more chalk and talk here, I'm just going to go through some of the implications of this. So let's say this is the set S. It has here 4 vectors, but we already know that there is the basis for R3 that is the standard basis, and that has 3 vectors. So S must be linearly dependent here. If I have a set for P3 that has 5 polynomials in it, then this can't possibly be a basis. Not to mention there's no x cubed in there, but it can't possibly be a basis because it's too large, right? Because the basises for P3 only have 4 polynomials, right? 1x, x squared, x cubed is enough, right? So in the standard basis, so this is already too large. It's linearly dependent. So the argument then is that if two sets are both bases for the same vector space, then they have to have the same size. How do we prove this? It's really simple. Assume that they don't have the same size, right? Well, then, since they're both bases, the size of one has to be less than or equal to the other. Same goes the other way around. The only way that both of those can be true is that if they have the same size. So in summary, a basis is a linearly independent set that spans a vector space, and all the bases of the same vector space have to have the same number of vectors.